thing. And we can talk about them as being innate responses and innate responses means any way the body protects itself from the time you're born. Okay, innate simply means that you're born with it. So it's things like being able to vomit or having diarrhea, anything that having intact skin. And these are sometimes also called non-specific responses because your body will vomit no matter what it is that you ate, etc. It's not tuned into anything specific. Okay, or we can talk about adaptive immune responses. Adaptive immune responses means your body has to learn. It has to be exposed to something. It has to recognize it as being non-self, and then the body's going to respond to that. So it's going to be specific. It means we have to recognize something that doesn't belong in the body. It has to be something that comes from the outside that doesn't belong to us. Now we have to be careful with that because that could be somebody else's too. It could be a transplant, right? It could be a bacteria or a virus, a toxin. It could be bee pollen. It could be all sorts of things. But your body's decided that I don't like it and I'm going to attack it. Anything that activates the adaptive immune response is going to be called an antigen. It sounds like a really vague definition, but an antigen is anything that the body is going to activate the immune response for, or the adaptive immune response for. Old books used to call this the immune system, and this simply defense mechanisms. But the latest vocabulary, everything is immune system. It's just innate, you're born with it, or adaptive, you had to be exposed to it and learn from it. Okay.
Is there anything that activates?
Anything that activates this, adaptive. Anything that we recognize as bad. So, non-self. Or, remember autoimmune, we've talked about some autoimmune diseases, so that could be that the body's tissue itself has changed just enough that you don't recognize it as self anymore. So there's a lot of things under this category that we'll talk about eventually. But let's start by talking about simply the innate, the stuff you're born with, the ability to do. I don't like this marker. And we can take the innate responses and talk about a first line of defense. So within our non-specific innate responses, simply having barriers. Like having mucous membranes. That's considered a non-specific barrier. It traps everything, stops it from going any further in the body. Clotting is a barrier, non-specific. Lots of things can cause the blood to clot, but it's a barrier and it stops just about everything from getting in. Various flushing mechanisms. Now we've mentioned vomiting. We've mentioned diarrhea. We can simply talk about urine flow. We can talk about menses, menstrual flow. All of these are simply ways of flushing the body of something. It's always hard to say this, but I'm fascinated with vomiting in the sense that I want to know how your body knows so quickly that you have to throw something up or have diarrhea from it. You go to a fancy restaurant and you don't even get a chance to get home. And you already know that there was something wrong in the food and your body wants to get rid of it. So that's, we don't quite understand how the body responds so quickly. What is the chemical message? So we have various kinds of barriers. That's your first line of defense. But probably the one we should pay attention to is simply intact skin. It's still a first line of defense. It's another example of a barrier. Okay, we're going to talk about skin, and this is a review from A&P1. It's a barrier in 3 different ways. It's a physical barrier. Not only because it's intact, but because it's layered. We get rid of the top layers and replenish it. It's made up of fairly impenetrable proteins called keratin. That's the stuff your hair and nails are made of too. If anyone has ever given the first time you gave someone an injection, you know that there's a real effort involved in penetrating the skin. There's a thunka effect there, kind of thing. So skin is a physical barrier. Skin is a chemical barrier. Anybody licked themselves lately? Or
To be honest, tequila shots,
actually
I
that's,
hope this part is clean.
well, we assume the
I
alcohol,
wash my hands.
the alcohol.
Yeah, that's cool.
Okay, congratulations, that is the very first time someone has given me that answer, kind of thing. I was gonna point out that perhaps you'd wanna lick somebody else, but anyway. What do you taste like?
So,
You're gonna have salt, and you're gonna be a little tangy with a hint of cherry wood, no. Kind of thing, salt, you're going to be acidic, and that's all because of sweat. Remember that sweat is a secretion that gets rid of, I hate to tell you this now, urea and uric acid. It also gets rid of sodium chloride, but in doing that, it creates a thin layer on your skin surface that is inhospitable to pathogens. Unless you're sitting here in a balloon in a sterilized environment, you're constantly being bombarded by pathogens from the last class that was in here, that left stuff all over the place, that's floating through the air. Just listen to that wonderful filtration system in the air. So, I mean, we're constantly being hit with pathogens, but they land on the surface. They find that it's unpleasant, it's too salty, it's too acidic for most microbes to live on. And so this acidity, this saltiness, is a desirable effect. We worry about people washing their skin too much. Okay? If you wash it too much, you remove what we call an acid mantle, this cloaking of chemicals that is antimicrobial. Now, who's suffering through microbe or has suffered through microbe? Aha.
thankfully.
At one point, you did a salt plate to see if there was a selective effect of microbes that could grow on a salty plate. And you found out there are 2 microbes. One is called Streptococcus epidermidis. Gee, I wonder why he's called that. And there's another one, Streptococcus aureus. And both of these have evolved the ability to live on a super salty or a super acidic environment. So they thrive on your skin surface. Okay? But they had to adapt, so they're unusual. Most microbes cannot survive in the acidity of the skin. But a third, so let me see, skin is a physical barrier, it's a chemical barrier, and it's also a microbial barrier. And a lot of students, when I ask this on an exam, they misunderstand what we're talking about, but we're talking about how do we use microbes to protect ourselves. These guys are what we call symbionts. That means those are microbes that we want to have living on our skin surface, because what they're going to do is they're going to keep the skin surface occupied. Okay? A symbiont is an organism that lives with us and doesn't do us any harm. He simply sits on the skin surface and keeps it occupied so that when the pathogens come, it's sort of like getting to the play late, there's no room. Getting to the game late, there's no room on the bench anymore, kind of thing, because all of the skin surfaces are occupied by these harmless bacteria. Pathogens, when they land, get pushed aside. They can't survive. So we want to encourage our skin to be slightly salty and acidic, slightly sweaty. We want to encourage our skin to have some microbes living on the surface, as long as they're not pathogens, as long as they're not doing us any damage. This is why we worry about people washing too often, using antimicrobial soaps, et cetera, this pathology of having to always be super clean and super amicrobial is actually doing damage, because you get rid of the symbionts, you get rid of that chemical barrier, and you're perfectly vulnerable to whatever comes next. So we really do have to worry about. Now, these two guys are interesting. Staph epidermidis, Staph aureus, classic microbes. They're fine as long as they stay where they belong. But if they get into the body tissues, then they become pathogens. You probably all know the variety of Staph aureus that is resistant to methicillin, a prominent antibiotic, and we call him MRSA. MRSA simply means methicillin resistant Staph aureus. Okay, so this is a methicillin, METH, as in penicillin, only it's methicillin. But this is a classic microbiology rule, that a microbe can be good in one place and bad, same microbe, bad in another place. So he's good if he stays on the skin surface. He's a protector. But once he gets inside the skin, then he becomes a pathogen. Okay? So you can't, with most microbes, say something is all good or all bad. In most cases, there's some good or some bad. So, we're still talking about our first line of defense, the various barriers the body throws up. Mucous membranes, blood clotting, flushing mechanisms, and skin. Physically, chemically, and microbe. How do we use the physical characteristics of the skin to protect us? How do we use the chemical characteristics to protect us? How do we use microbes to protect us? There's one other guy under chemical that we can add. Not only is the skin tough with the keratin protein, but the skin is also filled with a pigment protein, melanin. How is he protective?
Protects against UV rays.
Right, he's going to block the UV rays. Okay? So all of these are fairly, and you're born with all of this. That's why these are innate. They're going to protect us against all sorts of things, so it's not specific. It's just the way the body tries to protect us.
Could you go over like the MRSA and the methicillin resistant?
MRSA stands for methicillin resistant Staph aureus.
Okay, and is that a symbol?
That is Staph aureus that has become insensitive to most antibiotics.
Okay, so that's when it's in the body.
And, well, when he gets in the body, he's a pathogen. Most Staph aureus, you can just give yourself a good dose of antibiotic and you're good to go. But there's a particular strain of it that is resistant to most antibiotics. And if that's the one that gets into your skin, then you have a problem.
Okay, thank you.
Okay? We should all be very aware of MRSA. Andrew?
Is it the same thing as staph infection?
Andrew?
Is that the same thing as staph infection?
Not necessarily. A staph infection could be any, it's not necessarily this part. Right. It could just be any staphylococcus. Could be epidermidis.
Is that where is MRSA where they just, I guess, cut it out because there was nothing they can really do?
Most of the time, right. Because it's often not only just MRSA that it's resistant to, it's also resistant to some other antibiotics. Yeah, they try to. Okay, so our first line of defense is how do we protect ourselves on the outside? Second line of defense is also still innate. Okay. Innate has a first line of defense, and that's barriers. Second line of defense is going to be internal mechanisms. We're still innate. These are still things that you are born with the ability to do. For example, we all have populations of general phagocytes. Who are the general phagocytes we all have in our white blood cells? Just in case anyone ever asked. Neutrophils, monocytes. Now remember, when those monocytes move out, they can be called macrophages. They can be called dendritic cells. We see that term used in HIV studies, but it's simply another name for the macrophages. You know about it from skin. If anybody remembers the Langerhans cells, they run around in the epidermis phagocytizing things that don't look right. And in bone, we call them osteoclasts. Those are bone cells that went around eating debris from a break or just helping to clean things up. And in the nervous system, we call them microglia. So these general phagocytes, sometimes when they take up permanent residence in a specific tissue, we give them a specific name. But they're all just general phagocytes. I don't like the looks of you, I'm going to eat you. Yeah?
And you're born with them.
Yes?
They never.
Yes. So these are all still innate. Okay? Then we have a group of cells that break a whole bunch of rules. And these are still non-specific. So if we have general phagocytes is one type. A second type is what we call natural killer cells. Sometimes they're called NK cells. For people who are trying to save time. NK cells are actually lymphocytes. So that's one of the rules it breaks, because we said that lymphocytes in general are specific. They're going to become either T cells or B cells, but this is a third line that goes off to the side, and they're natural killer cells. The second thing that they do differently than everybody else is that they secrete and kill their pathogens with a chemical called perforins. And perforins, if this is my bacteria cell, this is my pathogen, perforins are little protein darts that poke holes in the wall of the pathogen, and he leaks out. We've never seen that way of killing it. We've eaten them, but we've never poked holes in them and just let them go. So natural killer cells was an interesting population of cells that we didn't realize existed for the longest time. Natural killer cells seem to be very good, specifically for intracellular pathogens. Natural killer cells seem to be best at finding cells that have a pathogen inside them. So that would be things like viruses, because remember, viruses go inside cells and hide inside the cells. For those of you that had suffered through micro, chlamydia is it's a bacteria, but it's so small that it can get inside a host cell and live inside the host cell, and nobody knows that it's hiding in there. Chlamydia. Get them?
No, just give it to me. Thank you.
And a third group of intracellular, inside the cell, is tuberculosis. The tuberculosis bacteria also gets inside cells and lives in there relatively protected, because the outside of the cell still looks like normal. But natural killer cells seem to be able to detect slightest differences in infected cells and say, aha, you don't look like everybody else, I'm gonna perforate and destroy you. Okay? So natural killer cells is our second type of internal, yeah,
But isn't that when TB comes out? Cause it's normally just like encapsulated, correct? And then
right.
if it were to open it up, then that's when TB spreads.
But no, but then he goes after the tuberculosis bacteria. What you're talking about more is when a person is in such poor health, like nutrition and stuff like that, the cells burst spontaneously and let the bacteria out.
Okay.
But in this case, I'm causing the cell to break, and I'm
And he's
sitting
gonna
right
eat it.
there.
Okay.
It's like eating the jelly out of the jelly donut. Third way, we're still in our internals, non-specific, and that is simply the body running a fever. Again, this is something every kid is born with the capability of doing. Just ask any mother or father who's taking care of a kid. Everybody can throw a fever, and there's lots of different reasons a fever is thrown. Okay. Fevers are going to kill in two ways. They're going to increase the body's defense mechanisms. It's going to make the phagocytic cells run faster, jump higher, eat more things. So when we increase body temperature, we make everything work faster. But the other thing, and I hate to go back to micro again, but it could have been in bio also. If we talk about temperature range for any organism, what we're going to find over a period of temperature over a period of time, if this is the number of organisms, we're going to find that we have, every species has a minimum temperature that they can live at. After, below that, they die. Then we find that as we get warmer, the curve goes up until we get to a maximum. Or not, sorry, not maximum, optimal temperature. For most pathogens, that's going to be 98.6. They just love living at normal body temperature. But then you'll see a sudden whoop, and that's the maximum temperature. After that, they die. All of human beings, and we've done experiments with this too. If you were to freeze a person, it takes them longer to die by cold. You heat them, they tend to become crispy and die pretty quickly. So this curve, this could be for an elephant, it could be for a human, it could be for bacteria. The curve's going to look the same. But if that optimal temperature is body temperature, and I just raise the body's temperature a couple of degrees, let's just raise the temperature to 100. Let's give them a fever of 100, 101. That's going to be enough to kill most pathogens. And that's what a fever does. He simply brings the temperature of the body up just enough to kill the pathogens rather than killing the human being. Okay? Now, we do have to be careful. So that's why a lot of times nowadays we tell people, leave the kid alone if he's running a fever. Make him comfortable, but let him run the fever. Because the fever will kill the pathogen. By killing the pathogen, by speeding up your defense mechanisms. What we have to worry about is when we get to the point where we're starting to kill human cells, when we're starting to denature proteins and enzymes and the various protein molecules we have. So we don't want to let the kid go too far. What do they tell you nowadays? 101? You call it 101? Oh, that's wimpy.
No, 104 is like hospital.
Whatever, talk to your doctor about it, but it's certainly, there's some tolerance. There's certainly a couple of degrees beyond 98.6 before we're going to let you worry about it. Now, in my expertise as a parent, remember when my kid was sick and she ran a fever, and I called the doctor in the middle of the night, And of course, there was some guy on watch, whatever you do when you're low man on the totem pole. And I said, I don't know what to do. My kid's running a fever of 108. And he said, you know, that's what he said over the phone. And I was surprised he was so upset. I mean, it was only 108. It was 100.8. When I said that, I thought there was just this dead silence at the other end of the phone. I thought he was going to kill me. Thank God he was at the other end of the phone. Kind of thing. Do be careful how you report temperature. But anyway, so that's what fever. Fever is nonspecific. Lots of people, lots of things will trigger a fever, and it's a way that anybody can defend itself. So fever is a second line of defense. It's an internal mechanism that we use to protect ourselves. Watch this guy. Inflammation. Now, inflammation's going to happen if we have a group of cells and one of them or some of them get sick. The damaged cell is going to release a chemical signal into the environment. They can be called leukotrienes, they can be called interleukins, they can be called all sorts of things. The one that we've studied best is histamine. So a damaged cell is going to release a chemical signal saying, I'm in pretty bad shape. Histamine goes out into the area and will do three things. It's going to cause a vasodilation. What are we going to vasodilate? We're going to vasodilate arterioles. We cannot vasodilate a capillary because it doesn't have any muscle. So we're going to vasodilate an arteriole. We're going to tell the capillaries to become leaky. We're going to tell the capillaries to lose more fluid out into the tissue because we're assuming that's bringing antibiotics, that's bringing nutrients, that's bringing oxygen. So get more leaky, let more things out into the tissue. And histamine is going to attract general phagocytes. Histamine simply alerts the environment that you have damage. Now, let's go back for a second because many of us know the first aid definition of an inflammation. And this is the same thing, only we said it from a physiological point of view. If I vasodilate blood vessels, I'm going to bring more blood into the area. So I'm going to get heat in the area and a redness or a darkening of the area. Okay? If I make the capillaries porous so that more fluid leaks out, I have swelling in the area. And if I attract general phagocytic cells after they're done, they all lay their dead carcasses, then we end up with pus formation. The general characteristics for inflammation: heat, redness, and pus formation. Heat, redness, swelling, pus formation. And it's simply explained by the actions of histamine. All the body's trying to do is bring more blood to the area, let that good stuff in the blood out into the tissues, and then bring the general phagocytic cells in. That's what an inflammation is. Yeah.
Why do the phagocytes like out?
Well, they die. Pus is simply dead white blood cells. Now, you get a sinus infection. Your sinuses get all inflamed. And what do you take? You take an antihistamine, which is sort of defeating the purpose. The body is trying very hard to protect itself, and you're trying to make sure you don't miss work. Kind of thing. So we fight against it. But inflammation is simply the body's, and remember, actually, I'm not sure whether it's 90%, but most of the world's population does not have access to aspirins or antihistamines. It said this is what the body does when you get an infection. Okay. You vasodilate arterioles, you increase the leakiness in the capillaries, you bring in the general phagocytic cells.
So what about people that have like immune diseases?
This isn't, well, it depends on what you're talking about. If we're talking about the autoimmune diseases, that's going to be, we haven't gotten there yet. Okay, we're still talking
Save
about
that for
general.
another day then.
Hmm?
I'll save that for another day then.
No, well, we'll get there, hopefully we'll get there tonight,
Oh, okay.
or next time. But right now, everybody can still become get inflammation. Oops, I didn't want to erase that. But number 5, in our ways that the body naturally protects itself. And this should sound familiar. Running around in your bloodstream is a series of proteins called complements. Thank you very much. Okay. We classify the complement proteins as C1 through C9. And this is another example of biological arithmetic.
You still on intact responses, right?
Excuse me?
I mean innate.
Innate, yes. We're all still innate. Okay. Running around in your bloodstream are a bunch of complement proteins made in the liver, normally not doing anything. They're just running around in the bloodstream, making it thick. Osmotic gradient, in case anyone ever asked you about what are the roles of proteins in blood plasma. There's another example. Okay, he's just making an osmotic gradient. But the complements, how do I want to do this one? Okay. When complements meet a pathogen, they can do one of two things. They can simply go over and lyse it. They can simply cut it up into little pieces. And we call that lysis. Just going to break it up into little pieces so the general phagocytes can eat it. Says, oh, I don't like you, chomp, 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 chomp. Okay? Or I can opsonize. The opsonin reaction is simply to sit and coat the pathogen. This is my pathogen. I'm simply going to coat it. By doing that, I make it more attractive to the phagocytes. To opsonize doesn't destroy the pathogen. He simply makes it more attractive to the general phagocytic cells. Okay, second perfect parrot story. Halloween. We're going to give out healthy treats. Well, my husband wanted to do apples. I said no apples. So I made oatmeal cookies. Healthy? Nobody eats oatmeal cookies. So I put M&Ms in oatmeal cookies. Then everybody would eat them. Destroyed any healthy benefit to it kind of thing. But that's what opsonizing is. Stud the surface with something that the general phagocytic cells will say, oh, that looks good, kind of thing, that they would otherwise have ignored. This is a good example. We're talking about tuberculosis. Tuberculosis bacteria has this nice waxy coat around it. Most phagocytic cells would say, oh, I'd rather not deal with some Vaseline-coated pathogen kind of thing. But if we opsonize it by putting complement proteins all over the surface of it, then the general phagocytic cells will say, oh, let's take a look at that. Chomp, chomp, chomp. So we're using a lot of vocabulary for different techniques. We've talked about perforating, cutting holes in it. We've talked about lysing, which simply means chopping it up yourself. And we've talked about opsonizing. These are two methods that these proteins that are sitting from the liver, running around the bloodstream, not doing anything until they meet something that doesn't look right to them, and then they attack. And they'll either attack by lysing or by opsonizing. Okay? Last, I think I might be up to 6. I might be making it up at this point. Is another natural defense mechanism that's a protein called interferon. And that's plural, because we're finding that just about every type of cell can make its own interferon. Interferon is a chemical that will attack viruses. Even though it specifically attacks viruses, it attacks any kind of virus, so we still consider it non-specific. We still consider it innate because everybody can produce interferon. Interferon works in an interesting way. If I have a group of cells and one of them gets infected by a virus, that virus is going to destroy that cell. He's going to make lots of copies of himself and he's going to destroy that cell. But while that cell is being destroyed, he in turn is going to release a chemical message to the nearby cells called interferon. Now, once the nearby cells have been treated with interferon, this virus still breaks up this cell. This virus still gets into these cells. But they can't replicate. They can't replicate. This is the Roach motel of immunology, kind of thing. The virus can move into interferon-treated cells, but they can't get out. And they can't divide. So what we've done is we've basically limited the viral damage. He's not going to get to any of the other cells in that area, in that organ.
So
Look-
sorry.
Okay.
So you're saying if a cell is infected with the virus,
Mhm.
then it'll release the interferon.
Right. And
Which-
warn his neighbors, but it's
Yeah.
not going to help him in the least.
Okay.
So it's a good example of altruism in biology, where that central cell is sacrificing himself for everybody else. Okay.
What a brave
Now-
guy.
Hmm?
So what a brave guy.
Might have been a female.
What a brave cell.
Better. Saved yourself.
I assumed his gender, I'm sorry.
No, I just shows our age sometimes. Notice about interferon though. No, interferon does not kill anything. And in reality, if we leave that infected area long enough, some of the viruses will start to move out. But what we've done is we've slowed the virus down. Viruses kill us because they replicate so fast and they do damage within 24 hours, 48 hours. Think of Ebola kind of thing. It just kills very quickly. If we can do anything to slow it down and give things like our general phagocytic cells a chance to catch up, then we've basically bought the body some time. And that's what interferons do. Interferons don't cure anything. Interferons slow the process down so that the other mechanisms can catch up, which I think is pretty clever in and of itself. What we do now is we have isolated, we can synthetically make interferon. It's just a protein. So we can synthesize proteins, have them in little jars, and inject people with interferons. Kind of thing. And we have been able to, people still die of rabies, but we've slowed it down, kind of thing. We've used it on HIV, and it slowed it down until the other medicines or the other therapies can catch up, kind of thing. So interferon is an antiviral process that the body can do itself. Doesn't kill the virus, but slows it down so that everybody else can catch up and do its thing. So that items 1 through 5 can catch up and do their thing. Yeah,
Can it slow it down to the point where if they decide to get it?
exactly.
You don't, but you don't.
The viral infection is destroyed, but not by the interferon. It's by the agents that
Also, I
have
can't
time.
destroy it.
Absolutely, remember, the interferon doesn't
Doesn't
do it,
do it, I know.
but it's everybody else that has the time to do it. So we're very excited about interferons, and if you give a patient an injection with a suffix of INF, that's an interferon injection that's going to help boost their defense mechanisms. Yep.
Is that what they give you, like, when you get, like, a needle stick?
No. Oh,
Like, in the hospital, like, say if you, like, go something, get a needle stick?
I don't know. I have no idea what they give you. Anybody know? I had an interesting dilemma once where I was woken up after surgery and asked if I would let them test my blood for HIV because one of the nurses had stuck herself. And I'm thinking to myself, nobody stuck themselves. I was aware of this procedure. There was no sticking. So I said yes to go ahead, test my blood all you want kind of thing. But I was worried if they had the wrong patient, who that nurse had been stuck by and whether she ever got identified. But I don't, that's a good question, I don't know. Homework assignment, Morgan. Does anybody know, seriously?
I can look it up.
No. You know, there is a regime in the school system where we collect the phones and we put them up front. Okay, so those are our innate defense mechanisms. The first line is external barriers, second line of defense is internal mechanisms, but they're all still innate or non-specific. So let's talk about adaptive responses. So now we're into adaptive immune responses. They're going to be different for several reasons. Number one, they're going to be activated by very specific agents. And you can throw up from anything. But your immune response is only going to be activated if it recognizes something and says, aha, this is a bad deal. Anything that activates the immune response is called an antigen. And as I said, that can be anything from a pathogen like a bacteria, virus, toxin, fungus, but it can also be tissue from somebody else. It can also be your own tissue that looks funny after an infection. So instead of saying this whole list of things that can activate the immune response, we simply say antigen. If your body overreacts to the antigen, we have an allergy reaction, and instead of being an antigen, we say that agent is an allergen. So for some people, something's an antigen, like peanuts. Well, actually, peanuts isn't even an antigen. Some things may cause a little bit of a reaction, but in other people, if it causes an explosive reaction, an allergic reaction, then we say instead of it being an antigen, it's an allergen. It's just a degree of response. Okay? Now, what's really interesting is there's something called a hapten. A hapten is a molecule that can stimulate your immune response, but only if it combines with a protein, a specific protein in your body. So a hapten has to mix with a protein in order to become an antigen. This is the variable. This is the variable. This is a molecule that if it happens to match up with a particular protein in your body, that complex becomes big enough to be called an antigen. Okay. Different people have different proteins. So if the hapten is, say, peanuts, most people don't have a problem with that molecule in their body. But if that protein goes into your body and meets a specific protein that's unique to you, the two of them get together and they become an antigen, and you have a reaction. So this explains why some people have reactions to molecules that other people don't. Some people are allergic to cat dander. Some people are allergic to grass pollens, and other people aren't. It's because when that molecule, that pollen or that dander gets into your system, it has to meet a protein that will combine with it and make it a big enough problem to become an antigen. So a hapten has the potential to be an antigen, but not all by itself. It has to combine with something else.
So if the hapten doesn't combine with a protein.
And go eat your proteins. Go eat your peanuts. Right?
But I'm saying, does that become an allergen then? Like,
No, this is what will become the allergen if you have a severe reaction.
if you don't have the protein though, what
If you don't have the protein, there's no reaction at all.
Okay,
It's
so-
just a small molecule, the body just, okay.
Alright.
So that's why, I mean, if you had the protein that can connect with the peanut oil or whatever it is in the peanut kind of thing, you eat a peanut, it meets that protein, and you end up with an antigen or an allergen. You don't have the protein in your system, you eat the same box of protein, of peanuts, you enjoy peanuts and don't die. Okay? That's what is interesting about it, is it's not the molecule itself that's causing the reaction, it's the protein that is unique in your body that matches up with that molecule that makes it an antigen.
And what makes something an allergen?
It's just when that antigen has a big reaction. It's like a whisper versus a yell, okay? Yeah.
Is that why some people can grow out of allergies?
We don't understand allergies to that extent. I don't think anybody, no matter how much they try, can explain allergy and allergy treatments. Some people will grow out of them, some people will acquire them. It's, depends on what school of thought. I think the most fascinating thing now is the treatment for peanuts in infants. Kind of thing where actually the American Medical Association has finally said, yes, feed your kids. Feed your little ones, like infants, the little tastes or smears of peanut.
There's kind of like an allergy runs in the family to give it to them while they're an infant. That way it can help prevent them from developing it.
Right. Because if, what we know about the thymus is, remember, it's youngest in little ones. So the more stronger your thymus is, and the more chance it has to recognize various things and say, oh, okay, that's just a peanut, kind of thing. Rather than wait till he's 6 or so and say, oh my God, that's a peanut, kind of thing.
They also have patches now that school-age children can wear so that they can be around peanuts if they have.
But that would be an antihistamine type thing. That would be an anti-allergen. Whereas what we're trying to do is teach the kids' bodies to tolerate it. You know, I have to stay. I mean, maybe I'm old enough. I think that's a brave parent. Yeah.
Yeah, I don't know.
Oh, I mean, they have it, they sell little kits, you know, a microscopic dab, a little bigger dab, kind of thing like that. So, and you're supposed to do it under the influence of or under the supervision of a medical person. But it just goes against what everybody has heard about how some of these things, and you're right, it's not just peanuts, it's
Yeah,
any
they're
kind,
saying
identify whatever it is. That would be interesting, it'd certainly be life-changing. So anyway, so this adaptive immune response is gonna require an antigen. I have to meet this antigen. It's not something I was born with. I have to be exposed to it, and I'm going to react to it. It's going to usually involve the whole body. Remember, an inflammation is just gonna be like, oh, there's where I got bit, type thing. It's gonna be localized. But adaptive immune responses usually get the whole body involved, so it's systemic. And then, very interesting, is that once you've been exposed to an antigen, your body is going to produce memory cells. And memory cells are going to help protect you the next time you see that antigen. Okay? I only wish that once the dog ate something disgusting and threw it up, he would remember and not do it again. But no, we'll go do it again. But with an adaptive immune response, I'm exposed to it, I develop memory cells, and I will be protected against from in the future. So let's see what's going to happen here. Well, we're talking about our lymphocytes. And we remember that lymphocytes all start in bone marrow as hemocytoblasts. And when the colony stimulating factor comes in and tells it to produce lymphocytes, we're going to find that there's two populations of lymphocytes. There's one population of lymphocytes that are going to pass through the thymus. And they're going to spend some time in the thymus getting educated. But when they come out, they're called T lymphocytes. They stayed up late thinking of that. They all get t-shirts now. The other group of lymphocytes that comes out of the bone marrow, we don't know what happens to them. And they're called B lymphocytes. T lymphocytes makes sense, thymus. B lymphocytes get their name because the first work was done with chickens, and with chickens, this population of lymphocytes went to an organ of the digestive system called the bursa fabricius. Problem is, humans don't have one. So we don't know where the B lymphocytes go to become B lymphocytes. A lot of people think it is exposure to things going through the digestive system. T lymphocytes, when they get activated, well, when T lymphocytes come out of the bone marrow and they've become T lymphocytes, what's going to happen is most of them are going to start to circulate through the body fluids. A few of them will end up in the lymph nodes. Oops. So I want to underline circulate. T lymphocytes tend to be the ones that we're going to find in blood. T lymphocytes are the ones we're going to find in any tissue sample. They're out circulating through the body. A few of the T lymphocytes will go to the lymph nodes and sit in the lymph nodes and do their thing. B lymphocytes, when they come out of the bone marrow, most of them are going to go to the lymph nodes and sit there quite happily. And only a few of them will circulate. And that's going to be important when we talk about function. So if you poke any part of your body, you're more likely to come across a T lymphocyte than a B lymphocyte, unless you had the luck of poking yourself in a lymph node. Yeah. T lymphocytes are general circulating white blood cells. When T lymphocytes get activated by an antigen, they are going to directly attack the pathogen. So we say that the T lymphocytes are involved in what we call the cell-mediated immune response. T lymphocytes directly attack If we directly attack the pathogen, we call it cell-mediated. The cells go out and just do their thing. Cell-mediated immune response. B cells, on the other hand, when they get activated, they all swell up and become what we call, unfortunately, plasma cells. When they've been activated, they all swell up and become plasma cells, and then they start to secrete proteins called antibodies. What's two more names for antibodies?
Can't say it, and
I know.
and
Gamma globulins and immunoglobulins.
Right?
It's all the same kind of molecule produced by activated B lymphocytes that became plasma cells that then start to secrete these proteins that we call antibodies. We can call them immunoglobulins. We can call them gamma globulins. All three terms are the same thing. When you get a shot of gamma globulin, you're getting a shot of antibodies. Anyway, so the B lymphocytes don't actually touch the pathogen. They just sort of say, oh, you go take care of it. So we say that the B lymphocytes participate in what's called an antibody-mediated immune response. An antibody-mediated, because he uses antibodies. In cell-mediated, the cells just go right over and smack them. But in antibody-mediated, the cells sit there and just ooze proteins that go take care of it. Now, that sounds nice and simple and straightforward. Unfortunately, the old name for antibody-mediated immune response is humoral immune response, because the proteins float through the fluids or humors of the body. To this day, many people use the term humoral immune response versus cell-mediated immune response, including nursing. No matter what we do, we cannot get the nursing people to move into the centuries in some terminology. So what we have to do is be aware that humoral immune response is the same thing as the antibody-mediated immune response. It's what the B cells do when they become activated. Okay? And the reason we need to know both is because you're talking to a patient who may know humoral immune response, but you may be getting instructions from a doctor that knows antibody-mediated immune response. So we have to be ambidextrous. Besides, antibody-mediated immune response was way too easy. So, let's see how this immune system, no matter which one it is, works. First thing that happens, da-da-da-da-da-dun-da-da. An antigen enters the body. This is how the immune system works. No matter which one we're talking about, whether we're talking about T cells or B cells. We start with the antigen walking into the body with appropriate musical background. Okay. First thing that antigen is going to meet is a macrophage, most likely. Remember the general phagocytic cells that are either sitting in your mucous membranes, they're sitting in your skin, they're sitting all over the place. So we're going to meet a macrophage, and the macrophage is going to eat them. Okay. Here's my pathogen, and I have little pathogen markers on me. Pathogen marker, pathogen marker. Here comes my macrophage. He's going to eat me. Right? The macrophage just ate him. And what the macrophage is going to do is after he's eaten the pathogen, he's going to take the markers from the surface of the pathogen and wear them on his belt. So now what we're going to get is a phagocytic cell that has little P markers on it. Here's my pathogen on the inside, all broken up, kind of thing. But I'm going to wear the P markers on the outside. So this cell is now called an antigen-presenting cell. I took the markers off the pathogen, I wear them on the surface, and I'm walking around sort of like the kid that ate chocolate cake and says, I didn't eat anything, but he has this big smear of chocolate around his mouth. Kind of thing. What cake? What pathogen? Kind of thing. Okay, he's an antigen-presenting cell. And he's going to wander around the body tissues until he meets a lymphocyte. Which type of lymphocyte is he most likely going to meet? He's going to meet a T lymphocyte, because those are the ones that are in circulation. I hate to be more gruesome. This antigen presenting cell reminds me of, and I understand this was a technique the French taught the Native American Indians, and that is when you kill somebody, you scalp them, and then you wore the scalp on your belt so that you could show how many people you killed. So it was really a French custom. We just blame it on somebody else. But that's what I mean. This is what that reminds me of. Oh, look at the pathogens I ate. Kind of thing. Antigen presenting cell. Okay, the antigen presenting cell is going to wander through the body until he finds, most likely, a T lymphocyte. Oops. Now, he could bump into a whole bunch of T lymphocytes until he finds the T lymphocyte that's going to recognize that pathogen. Oh my God, you ate that one? Kind of thing. In which case, that T lymphocyte, once he's been activated, the T lymphocyte recognizes the markers. He's going to get hysterical and what we call proliferate. He's going to proliferate. When you meet the right T lymphocyte, the one that recognizes the markers you're wearing, that T lymphocyte makes hundreds, I can't do that on the board, hundreds of copies of himself. He proliferates and makes hundreds of copies of himself. Some of these cells, some of these new T lymphocytes, are going to get put aside as memory cells. They're not going to do anything else. Some of them are going to be called cytotoxic, or I prefer the term killer T cells. Because they're going to go out and they're going to attack anything wearing those markers and kill it. Then we're going to have a group of cells that are called helper T cells. Now, different books have slightly different names for some of these guys, but they all have the same rules. A helper T cell is going to do two things. A helper T cell is going to tell you to make more but it is also going to go activate nearby B lymphocytes. The helper T cell is the cheerleader, is the alert, is the alarm that's going to activate more T lymphocytes. He's going to also tell the B cells, why don't you wake up and get straight. And there's one more population of cells that we're sort of interested in these days. The last population of T cells are called regulator T cells. And their job is to, after the body has activated, after we've attacked the pathogen, the regulator T cells come in and say, there, that's enough. They're going to limit the immune response. They're going to prevent it from becoming an allergy response. They're going to say, he's dead. You've killed him. Enough. Don't keep going. Regulator T cells put the brake. Now, why are we interested in these populations? Because obviously people who have allergic reactions don't have regulator T cells working. So if we could, despite the fact that we're going to have people eating peanuts now, if we could figure out a way to make these guys more effective, we may be able to limit allergic or overreactions to things. So T cells, when they get activated, put some memory off to the side, put some killer cells out there to go out and attack, and put out some helper T cells to boil more T cell reaction, and we're going to have regulators to slow it down, say there. Now, HIV, tissue of preference is this population of cells. HIV likes to kill those cells. Look at what that does to your immune response. We're going to suppress the T response, and we're going to shut down the B cell response. The B cells will never know. Helper T cells is the perfect target for a pathogen. I'm going to slow down the T cell population from responding, and I'm going to shut down the message to the B cells. It's a classic military action. If you're going to attack the enemy, go for their supply line, go for the communication system. That way, they just totally don't mobilize. And that's what HIV does. Okay. Let's just finish off this and then we'll quit. So, meanwhile, back at the B cells. Here comes the helper T cells. They're going to find some B cells. And once they found the B lymphocytes will do the same thing. We'll proliferate. We'll make lots of copies of it. Oh, so excited, so excited. Something to do. So we're going to make lots of copies of our B lymphocytes. Again, some of them are just going to get put on ice as memory cells. But everybody else is going to become plasma cells. And as plasma cells, they're going to start producing antibodies. The cell-mediated immune response involves killers, it involves helpers, it involves regulators. The humoral immune response just involves antibody production. Both systems are going to set aside this mysterious population of memory cells. In reality, that's what's going to save your life. But we'll talk about that next time. Okay, so we'll finish off the immune system. Everybody can take a deep breath, because maybe we'll get to start the respiratory system.
Are you saying that the helper cells become B lymphs?
No, they wander through the body tissues until they find some B lymphocytes. Remember, they're in the body fluids, so they're most likely going to get dragged into a lymph node. And who's sitting in the lymph nodes? The B lymphocytes.
No, you're not doing it. That's why.
For some reason, guys, the textbooks like to talk about B lymphocytes a lot and T lymphocytes a little. But 90-something% of the B lymphocyte activation is caused by T lymphocytes. So it only makes sense to talk about these guys first. They activate the B system.
This part here.
That's your
That's the
macrophage.
macrophage.
And he's phagocytizing, so he's going to engulf it and eat it.
All right, and this is the
This is the pathogen, but he's got little markers on it.
okay. And then so the macrophage is engulfing it.
Right?
This is the next.
And then
step,
he's
like
going to take the little pieces off the outside. It's like if you stole somebody's beaded purse and then wore the beads on yourself.
Okay.
That's what he took it in, he destroyed the pathogen, but he's wearing his markers on the outside. So that's how I know he ate.
I mean, it sucks.
That's the destroyed pathway.
Right.
And then it takes the markers,
And then that's how the T lymphocytes are going to know who he ate.